So welcome to lesson 3.7, which is all about statistics and correlation. Now, as theoretical historians, we're going to be looking at patterns in our data, and we want to know what kind of patterns we're looking at and whether those patterns are meaningful. And that's where statistics comes in. And a key type of pattern that we might be looking at is the idea of a relationship between two variables. So, for example, we might have collected data for a particular country on the number of riots per decade. So let's draw that chart. This represents the number of riots per decade. So sometimes the number of riots is high, sometimes it's low. And for this country, we might also have collected data on the price of wheat. So let's plot that on the same chart. So here is a chart of the price of wheat, and we might look at that and say it looks as though there's a correlation between these. As the price of wheat goes up, the amount of rioting goes up, and when the price of wheat goes down, the amount of rioting goes down. So the two things are related, because when the price of wheat is high, it means that people can't afford much wheat, so they feel poor and unhappy, and they're more likely to riot. Whereas when the price of wheat is low, people can easily afford wheat, and so they're less likely to come out and riot on the streets. So we're hypothesizing that there is some correlation between these two, and what we would then want to do is for sort of each pair of points by each decade, plot the price of wheat and the riots per decade against each other. So we'd have a scatter plot. So there is the price of wheat and there is riots, and we plotted the two things against each other, and we might be tempted to draw a line through the points and say, you know, it certainly looks as though these two things are correlated. But what we want to know is, you know, is this correlation meaningful? Could this just have arisen by chance for this particular set of data? And another thing we might want to do is say, well, you know, insofar as there is a correlation, because it certainly looks as though as the price of wheat goes up, the amount of rioting goes up, it explains some of the variation in riots, but also, you know, we can sometimes have more riots than expected and sometimes fewer riots than expected, as it were. So the price of wheat only explains part of the variation in the amount of rioting. And what we want to do is quantify that. How much of this variation in the amount of rioting is explained by the price of wheat? And if we find that it's 60%, then that leaves 40% that's unexplained by the price of wheat, and that encourages us to look for other factors that explain the residual variation in the amount of rioting. So that is all the topic of correlation. And in this lesson, I'm going to be discussing various statistical techniques and deriving them somewhat from first principles, just to show where the ideas come from. But in reality, you wouldn't do these calculations manually, or, you know, using the formulas from first principles. You would use statistical software to do it for you. And you've got three options there. The first one, which is the main one that I would use, is Excel spreadsheet. It's got lots of statistical functions built into it, and it's fairly easy and intuitive to use. Another option, though, is specialist statistical software. So, for example, there's something called SPSS, Statistical Package for the Social Sciences. I think that's what it stands for. And also something like Wolfram Mathematica. So SPSS is specifically devoted to statistical calculations. Mathematica is devoted to all kinds of mathematics, but it has very sophisticated statistical functions built into it as well. So you could use these, but these are, you know, proprietary and paid for, so you'd need to buy them if you don't have access to them. And then there are free statistical software packages. The main one is R, and there's also something called Weka, which is developed by a university in New Zealand. And this is specifically for statistics. This is for machine learning and statistics. It's got a lot of statistical capabilities built in, but it also does machine learning, which is that you can throw at it some data and ask it, automatically to extract the patterns from the data. So both of these are free, and both of them have a lot of documentation online and forums devoted to them. So it's very possible to come up to speed on how they work. Now, in this particular lecture, I'm going to concentrate on the idea of distributions. So by distribution, we mean the way the values of your data are distributed, the pattern in the values. So whether, for example, they're spread out or bunched up. And there are three sort of topics I'm going to divide this into. Firstly, we'll look at the idea of moments of a distribution. So these are a way of quantifying the pattern in the data, and the two ones we will be considering, the two main ones, are the mean or the average of the values and the variance, how spread out or bunched up they are. Then I will look at some particular distributions that we're likely to come across in theoretical history: the normal distribution, the Poisson distribution, power law distributions, and the log normal distribution, all of which we've touched on already in this module. And lastly, I'll discuss the idea of hypothesis testing. So this is a situation where you've got two sets of data and you want to know whether they are drawn from the same underlying distribution or whether they're necessarily drawn from different distributions. So it might be, for example, that you've collected data on religion versus political institutions. So you might have a sample of Christian countries and a sample of non-Christian countries. And you find that in the Christian countries, you have quite a high proportion of democracies, whereas in the non-Christian countries, you have a lower proportion of democracies. And so you might have the theory that Christian countries are more likely to be democratic. But the question is this a genuine relationship, or could this just have occurred by chance, that just by chance these Christian countries, the sample that we've taken, just happen to have more democracies in them? So you're asking, are Christian countries, do they have a higher probability of being democratic than non-Christian countries, or is the probability the same for both, and it's just by chance that we've picked up this difference? That is hypothesis testing, and we'll be examining how that works. Okay, so I said I'd start with the idea of moments of a distribution. And here are two distributions. We've got sets of data that have a value x is the variable measuring our data, so whether it's riots per decade or price of wheat, whatever it is. And I've shown them on this line of x. So these are the different possible values of x in this distribution, and here are the different values we find for our data in x in this other distribution. And there's a difference between them. And the first thing we would notice is that they've got different averages. This one seems to fluctuate around somewhere around here. That's the mean, for which we can use the symbol mu, the Greek letter mu, Greek letter m. The mean. Whereas here they're fluctuating around a higher value, a higher mean value. And the other thing is that this distribution is more spread out than that one. So this is the variance, V. So this distribution has a larger variance than that one, and this one has a higher mean than that one. Now, to calculate the mean, it's something we learn in school, fairly basic. We add up the values and divide by the total. So if these values here are x1, x2, x3, all the way up to xn, then the mean is just x1 plus x2 plus x3 plus all the way up to xn divided by n, the total number. And we can write that more simply as the sum as I goes from 1 up to n of xi, and then divided by n, the total number. So, we've seen sums before. That just means we put in all the values 1 to n for the I, and we then add them all up, and then we divide by n. That's just saying the same thing. And this is the mean. It's also sometimes written as x bar, the average x, the mean x. And what it means basically is this is the value that the variables would have if they were all the same, but gave the same total. So it might be, for example, a country collects tax from all its citizens, and people pay different amounts of tax. But if everybody paid the same amount to give the same total, the mean is what they would have to pay if everybody was paying exactly the same to add up to the same ultimate value. That would be the mean. So it's kind of what the average person is paying, what the typical person is paying. And also then if we started with everybody paying the same, but some people pay a bit more than the mean, then there must be people on the other side who are paying less. Because if we add people who pay more, then it would change the value, increase the total. So we must have some people paying less to bring it back down to the same total. So there will be the same amount above the mean as below the mean. So that's our formula for calculating the mean. And then for the variance, well, we're interested in how far the data lies away from the mean. So here the data, the values can be very far from the mean, whereas here the values are all very close to the mean. So what we're interested in is the difference between the values x and the mean. That's the difference between them, x minus mu. Only we don't just want to find the average of those, because some of those will be positive and some will be negative. So if we sort of start adding them up like this, then the ones that are on the positive side of the mean will cancel the ones on the negative side, and we won't get anything. It will just add up to 0. So what we could do is take the absolute value, so that we're not interested whether it's positive or negative. We just take, we treat everything as positive. So that's what's represented by the absolute value. But it's difficult to work with the absolute value mathematically. So what we do is we just square that and the square is always positive. And then we just find the average of the square of the distance from the mean. So we're just going to add up all those. So we've got xi, each value x, from 1 to n, and then we divide by the total number n. So that is the basic formula for our variance. We're adding up the squares of the differences from the mean and then dividing by n to find the average squared value. But we can simplify this if we expand that bracket. Okay, so that's the normal rules of multiplying out a bracket. We'll get that. And then we can take each sum separately. So I've just taken each term there and taken it out, summing up each one individually. So the first, should have put divide by n in front of all of them. So this is 1 over n, the sum of the xi squared. This is minus 2 mu over n times sigma xi. And then this is plus mu squared over n times the sum of 1. Now, if we look at this, this is the average of the xi's squared. So it's xi squared, and we're finding the average, adding them all up and dividing by n. It's just the same as finding the average of the x's here. Here we're finding the average of the x squareds. So that's xi squared bar. Same as here, this was just x bar. And then, and in fact we don't really need the I, do we? And now here we've got 2 mu times 1 over n times the sum of xi. Well, that's just the same as this, 1 over n times the sum of xi there. So, which is mu. So this is mu times 2 mu times mu. And 2 mu times mu is just 2 mu squared. And then here we've got mu squared over n, and then we've taken the mu squared out because it's a constant from inside the sum. So we're just adding up a load of 1s, and we're adding up n of those because we're summing over n. So n lots of 1 is just n. So that n will cancel that n, and we're just left with mu squared. And so we've got minus 2 mu squared plus mu squared. Well, one of the mu squareds cancels, so we've got x squared bar minus mu squared, which we could also write as x squared bar minus mu is x bar squared. So that is the variance. It's a simpler way of calculating it. We just find the average of the x squareds, and then we take away the square of the average, or the mean of the x. So let's write those up again. Define the mean by that, and with the variance, n is defined by that. But the variance is is the square of these differences. What we can also do is take the square root of this, which will give us a better feel for the actual distances involved. Because as I say, these are squared differences. So if it's 2 away, it will be 4, and if it's 3 away, it will be 9. But if we take the square root, we're getting a better feel for the actual distances involved. And that is the standard deviation, which is normally written with the Greek letter sigma, small sigma. It's the square root of the variance. So here are our key statistical metrics to reflect the two patterns in the differences in these two patterns of the distribution of the data. And now what we'd normally do is not, draw our values out like this as dots on a line, would we? But we would make a kind of a histogram, say for this, so we'd have something like that. And then here are our possible values, x1, x2, x3, etc. And the height of the bar is the number of data points that have the value x1. And then there's n2 that have the value x2, and n3 for x3, and so on. So when we're finding our mean, x bar, we could write that as x1 plus x1 plus x1. Let's say n1 is 3. There were 3 with value x1, and then let's say there were 5 with x2, so that would be plus x2 plus x2 plus x2. And then for x3 and so on, and then we divide all that by n. That's an n, not a mu. But clearly we wouldn't want to do it like that. We would just write n1 times x1 plus n2 times x2 plus n3 times x3, and so on. So in other words, it would be the sum of ni times xi divided by n. And then we could take this, should just note, in this case n is equal to the sum of the ni. It's all the different numbers here added up. So this is not x1 to xn now. N is, the capital N is the sum of all these different numbers. That's a total amount of data. But anyway, so the x bar is going to be 1 over n sum of ni xi. And I was just saying we can take the n inside here to write it like that, ni over n times xi. Now ni is the number of data that had this value x1, and n is the total amount of data. So this is the fraction of the data that has the value x1. So if you've got 100 data points and n1 is 3, that means 3 out of 100 had the value x1, and we can write that as the we can call that the frequency of the value x1 in the data. It occurred 3 times out of 100. That's how frequent it is. That's the frequency of the data. So we can write that as the sum of fi, f for frequency, times xi. And then the point of all this is that if we go to a continuous variable, so instead of it taking on discrete values, 3, 4, 5, or whatever it might be down here, it varies continuously, so it can be any decimal number. We're not going to be able to add it up because, for continuous variables, they can take on, infinitely many values between the points. So we would go from a sum to an integral, and we're still going to have xi, though we won't put a subscript on it at the moment, because give myself a bit more space. We won't have a subscript on it now because it's not discrete values, it's varying continuously, and we want the frequency the proportion of the variables that have that value x. Well, for the frequency, we now need to take the probability density function, which is saying, so if this is a continuous variable, the probability density function p of x tells us what the probability is of finding it at each value x per unit length along here. To get the actual value at x, we multiply the probability density times the tiny infinitesimal distance around x dx. So we would replace the frequency with p of x times dx. So that's the kind of the fraction that are around x, that are between x and dx. And then we multiply by x, same as before, and then we would add all that up, or in other words, integrate over all of x. This sort of upside down A symbol means for all x. So we integrate over all the possible values of x, which might be from 0 to infinity, or minus infinity to plus infinity, or 0 to 1, whatever it is, whatever values x can take on, we integrate over all the possible values of x. And we just tidy this up because, you know, we'll represent it by the usual way of writing an integral, which is to put the dx at the back there. So we put p of x times x dx. So for a continuous variable, that is the formula for the mean x bar. And then if we want to find x squared bar for a continuous variable, because remember we need that to calculate the variance, that's just going to be the same thing, the sum over, or the integral rather, over all possible values of x, p of x times x squared dx. And these are the moments of the distribution, or at least could say these are the raw moments. And then we can have higher moments, because if we had x cubed, that would be the next moment up, and we can have x to the fourth and so on. We have x to any value. These are just higher moments of the distribution. But we wouldn't necessarily call this the moment. We would sometimes call v is the moment of the distribution, the variance. So it's not actually this, it's this minus x bar squared. So if we want to call the mean and the variance the moments, the mean is that moment either way, but if we want the variance, if we would call the variance a moment, then we would need to subtract x bar squared. But that's just terminology, whether you call that the moment or this the moment. And then, as I say, there are higher moments, so we could have p of x with x cubed, and that x cubed gives something called the skew. X to the fourth gives something called the kurtosis. But the skew is defined not just as integral p of x cubed dx, but as something a little bit more complicated, the same way that variance is a little bit more complicated than just the integral of x squared. We have to add, or as rather subtract this. Similarly for skew, there's a formula that depends on the standard deviation, for example, but and similarly for kurtosis. But what skew measures is whether the distribution is very symmetrical or whether it's sort of more bunched up on one side and more spread out on the other. So the first one I drew there, that's, you have a very low skew, and that one has a high skew. You can find that by using this moment based on x cubed. but you know, they're not really very commonly used, and we won't be using them. So those are the moments of a distribution. Okay, so I said we'd look at 4 particular distributions, and we'll start with the normal distribution. And what I put up here is something that we saw earlier in this module, the idea of throwing 2 dice and looking at the total score. And we saw that it can vary between 2 and 12, but the most likely outcome is a 7, a score of 7. And we can, well, what we're measuring up here in this chart is the probability or the frequency, if x is the score, or the frequency of x. If we actually did this as an experiment, we would expect to find something like this, or the probability of finding these particular scores. And in fact, for a score of 7, it's 1/6, and for a score of 2, it's 1 in 36. 36 different ways the dice could come up, and only one of them, 2 1s, gives a 2, and similarly only one of them gives a 12. So those are both 1 in 36, and 7, there are 6 ways it can become a 7, so 6 out of 36 is 1/6. And the probabilities decrease linearly in fact, so this is a 6, this is 5/36, 4/36, and so on down to 1 in 36. So that kind of goes straight up and down. If we throw 4 dice, we find here that the value of x can be between 4, that's if they all come up 1, and 24 if they all come up 6. And again, what we're measuring up here is the probability or frequency. And the most probable outcome is 14. The actual values up here are not the same as there. It doesn't really matter what they are. But we find that, so the most common value is 14, and they vary on either side of it, similar to that. But these aren't straight lines now. Sort of more, there's a bit more of a bend to it. And if we then throw 10 dice, again we've got P of x or f of x up here, and x along there, it can vary now between 10 and 60, 10 1s or 10 6s. And the mean, the most likely score, is 35. And what you may notice here is that we're actually getting that familiar bell curve of the normal distribution coming out of the probabilities. And indeed, what we find is that the more dice we throw, the closer it gets to a normal distribution. And a normal distribution arises in cases where the value of a variable, in this case the score, depends on many independent random factors. So in this case it's depending on 10 random factors, the score on each die. But for something like people's heights, which follows a normal distribution, we can say it's a normal distribution because it depends upon a large number of factors, all of which can take on different random values. So it might be, depends on multiple genes and multiple environmental effects, and all those can vary randomly, but their net effect is to produce a normal distribution. And we don't need to draw a histogram per se, because these the heights of the bars are just the value, the probability, or the probability or frequency. So we could just kind of get rid of that, all those bars, and we just plot the actual values. So let me draw that out again here. So this is our normal distribution. It has a mean value, the most common. It's the most common, and then it can vary on either side. And what we find with the normal distribution is that if we go within 1 standard deviation on either side of the mean, it turns out that 68.3% of the values will lie within 1 standard deviation. So in this case, well, it's with 10 dice, so it's only going to be approximately a normal distribution, but 68.3% of the times we will get a score within 1 standard deviation of 35, the mean. And then if we go to 2 standard deviations on either side, we find that (95.5%) of the values will lie within 2 standard deviations of the mean. And then within 3 standard deviations, it is 99.7%. So if we have people's heights or the scores on the dice, then 99.7% of people's heights or 99.7% of the scores will lie within 3 standard deviations of the mean. That for an exact normal distribution. And the formula for this curve is e to the minus a half x squared, or it's proportional to e to the minus a half x squared. There's some constant in front, doesn't really matter what it is. But the shape of the curve is defined by this as e to the minus a half x squared. So it decays exponentially with the square of the distance away, the square of x. And you can see that for this, in fact, the mean value is going to be 0, because if x and minus x are going to give the same value, because x squared and minus x squared are the same. So x and minus x will give the same value here, so this will be symmetrical on either side of 0. So this applies when the mean is 0 and also when the standard deviation is 1. That will gives you that'll be the case when when this is described by e to the minus a half x squared, if x is along here. In the general case, where the mean is not 0 and the standard deviation is not 1, but there are mu and sigma, it's proportional to e to the minus a half z squared, where z is given by x minus mu over sigma. It's the distance of the value from the mean converted into standard deviations, the number of standard deviations from the mean. So you can see that if we take not x but x minus mu, that will just shift the whole thing along to mu, because now it will be symmetrical about mu. Also, if we divide by the standard deviation, that means that if it is 1 standard deviation, then that becomes divided by a standard deviation becomes 1. So it will be corresponding to this same curve, the curve that's centered on 0 with a standard deviation of 1. And this is the point of doing this, is that we can then sort of compare data in a standardized way. Instead of talking about the actual values x, we just talk about how many standard deviations the value is from the mean, and the behavior of that is the same for everything that is normally distributed, because the chance of it being 1 standard deviation from the mean is always 68.3% if it's normally distributed. So we can, by converting it into this value z, instead of talking about x, we talk about z. We can say, you know, if it's 1.5, then we are saying it's somewhere between, well, it's halfway between 1 standard deviation and 2 standard deviations, and so we can say how likely that is to occur. And you sometimes hear then, for example, people talk about a 6 sigma result, meaning it's very unlikely. So you can see here that with 3 standard deviations from the mean, it's already 99.7% is within 3 standard deviations. So only 0.3% of the time will it be larger than 3 standard deviations away from the mean. So you can imagine that getting out to 6 sigma, the chance of that is very, very low indeed. So something like the CERN particle physics experiment, they may talk about a 6 sigma result. What they mean is that they're finding something occurred that has a value that, if this were just a random variation around the mean, the chances of it are that it's 6 standard deviations away from the mean. So the chance of that occurring is so low that it doesn't seem likely to be just a chance result. There must be some other process going on to cause it to get to that value, because it just is impossible to imagine that it could be so many standard deviations away from the mean. And so yes, to clarify that, then there's a bit more what I was saying is that the Z value would then be 6. So we don't need to worry about what the actual value that they're finding in the particle accelerator is, what the actual value of the measurement. They've converted it by this into standard deviations, and so it's 6 standard deviations. Well, we then immediately know that that is extremely unlikely. Okay, the next distribution we'll talk about is the Poisson distribution. This occurs in the situation where something is happening at a particular average rate, but it can vary around that rate. So just to put it in concrete terms, it's like cars coming down the road. There are so many cars will appear per minute. So there's an average, let's say 3 cars per minute, but they're nevertheless coming randomly. So some minutes you might get only 1 car or even no cars, and other minutes you might get 6 cars. So on average there's 3 cars per minute, but it can be more or less than that. And the Poisson distribution looks like this. So it has a certain mean, and which I said, for example, might be 3 cars per minute. And it could be less than the mean, or it could be more than the mean. So we could only have 1 car per minute, or no cars per minute, or we could have 10 cars in a particularly busy minute. And what is found is that the variance of a Poisson distribution is equal to the mean of the Poisson distribution. And the reason we, as theoretical historians, are interested in this is that some people have been talking, for example, about the fact that we've gone a very long time without any major wars. Since the end of the Second World War, has been 80 years now, and there's been no major wars. And some people have suggested that this shows a major change in history, that either because we've got things like the United Nations and we're more enlightened now, or because of nuclear weapons which have made war between the great powers unthinkable, that we're no longer going to have major wars. Major wars just won't happen, and differences will be resolved in other ways. So there is this argument that this is history has changed in some way. We no longer will have major wars. Well, as theoretical historians, we need to be able to test claims like this, because we want to say, well, yes, we've gone a long time without any major wars, but it might be that it's something like this Poisson distribution, that we could have a very long gap between the cars just by chance. Yes, the cars are coming along at a certain rate, but sometimes you might go a minute or 2 without any at all. And the fact that we've gone 80 years without a war, is that really due to a change, or is it just because the wars come along at random intervals? They're bare Poisson distribution, and we just happen to have be going through quite a long interval, but eventually their wars will occur again. there's a big question there. Is this a real change in history, or is it just an illusion? And so we need to understand the Poisson distribution so we can test statistically that gap of 80 years and say, given what we know about the rate at which major wars have occurred in the past, is a gap of 80 years enough for us to say something has changed or not? So that is why we want the Poisson distribution, or need to know about it. Okay, our next distribution is the power law distribution, which has the formula that the probability of the variable having the value x is proportional to x raised to some power, x to the minus alpha. Alpha is the exponent of the power law, and c is some constant in front of it. So that is, it describes a power law, and we saw that power laws, are pretty common in socio-historical data. For example, the sizes of wars obey a power law. The larger the war, the less likely it is, and there's a power law relationship where, in this case, x would be the size of the war, and p of x is the probability of a war of that size. Now, if x were to be 0, x to the minus alpha would be would be infinite, because x to the minus alpha is the inverse power of x, so it would be 1 divided by 0 to the power alpha, which is going to be, well, 1 divided by 0, infinite. So we can't have values of x equal to 0, so there must be some lower bound. x0 for a power law. It can't get down to 0, but it goes down to some lower minimum value, x0. And we can then find the mean value for the power law using the formula we had above. So it was p of x times x dx. That's the standard formula for the mean, which we showed where that came from, and we would integrate that from x0, the lower bound, the minimum possible value, up to infinity. In principle, x could be as large as infinity. The larger it is, the less likely it is, but it could go up to infinity. And we're going to replace p of x with cx to the minus alpha. So that's cx to the minus alpha times x. Well, x times x to the minus alpha is x to the 1 minus alpha. So it was x to the 1 times x to the minus alpha, which, just applying our rules for exponents, becomes x to the 1 minus alpha. So to find the mean, we just have to solve that equation, do that integral. And so we do it in the usual way. We can bring the constant out. And to integrate x to the 1 minus alpha, you may remember, you should remember from calculus part of the course, that if you've got x to the n, it goes to 1 over n plus 1 times x to the n plus 1. That's the n plus 1. That's the antiderivative of x to the n. So in this case, n is 1 minus alpha. So n is 1 minus alpha, so 1 minus alpha plus 1, so that will be 2 minus alpha. 1 over 2 minus alpha, and again n plus 1 is 2 minus alpha, so x to the 2 minus alpha. And we're going to calculate that between x0 and infinity. Now, let's say if 2 minus alpha is greater than 0, 2 minus alpha is greater than 0. Well, this will be positive then. 2 minus alpha is greater than 0. In other words, it's positive. So it'll be infinity raised to a positive power, which will be infinite, squared, or infinite raised to a positive power. So that will also be infinite. So if 2 minus alpha were greater than 0, mu would be infinite. And if 2 minus alpha, so if 2 minus alpha equals 0, then we'd be dividing by 0 here. So again, we'd have mu being infinite. Or strict mathematicians might prefer me to say it's undefined in these cases, but we don't have a mean. We can't really have a mean of infinity. So in other words, if 2 minus alpha is greater than or equal to 0, we don't have a mean. 2 minus alpha greater than or equal to 0 implies no mean, no meaningful mean, or an infinite mean. Or in other words, if 2 minus alpha is less than or equal to 0, in other words, if alpha is less than or equal to 2. That implies no mean. And for Zipf's law, alpha equals 2. You may remember that on the rank size plot, which when I talked about the power laws, we used the name beta for the exponent of the power law. That is equal to 1. That is Zipf's law. It is found, for example, in cities or in the frequencies of words in language. So beta is 1, and when beta is 1, the exponent of the probability density function alpha is 2. We derived and showed that earlier. So anyway, for Zipf's law, alpha equals 2, which means that there's no mean. So for things like the population sizes of cities, in terms of the underlying distribution, it doesn't have a mean strictly defined if it obeys Zipf's law. In fact, it breaks down because there's the population of the country, so that that sets an upper bound, so we can't really go to infinitely sized cities. But yes, with Zipf's law, because arbitrarily large events can occur, then there is strictly no mean, or the mean is infinite, or we say sometimes the mean diverges. And I talked earlier about how this is a problem in the stock market, where if you assume that the variations of fluctuations in the stock prices obey a normal distribution, then you can say, oh well, a 6 sigma result is extremely unlikely, so it's going to stay within the 6 sigma, or probably with 99.7% of the time it's going to stay within 3 sigma. But if it's not normally distributed, if it's a scale-free phenomenon, if it obeys a power law, then there is no mean. There is no average value for the fluctuation, and the fluctuation can be as large as you like. And the longer you wait, the bigger event you will get. And so the risk is, the risk is infinite, because the size of fluctuation you can get on average has an infinite average. Okay, and for the last distribution we'll consider, I said, would be the log normal. So the idea here is that if we've got a normal distribution, in this case we've got it centered on 0, and the values here are going 10, 20, or minus 10, minus 20. So we know with normal distribution that it falls off pretty quickly once you get beyond the standard deviation or so from the mean. So if we've gone from 0 to 10 here, roughly 1 standard deviation, and 20 here, then to 30 or 40 is very, very unlikely. So most of the values are going to be pretty close to the mean. With it's from 10, it might be double that, it might be treble that, but it's not going to be much beyond that. But with a log normal distribution, we regard this not as the variable x along here, but as the log of x. So these values are logs, and the actual value then will be the inverse of the log. So x will be e to the 0, e to the power of 10, e to the power of 20. Because that's x, the logarithm of that is 20. Well, I put log, L-O-G. I suppose strictly should put natural logarithm. But that's just a notational thing. But so yes, the logarithm of e to the 20 is 20. The logarithm of e to the 10 is 10. So x varies. So e to the 0, e to the 10, e to the 20. E to the 0 is 1. E to the 10 is about 22,000. And e to the 20 is about 500 million. So if we treat these as logs, the values of the actual variable can vary by a much greater amount than when it's just obeying a normal distribution. Going from 1 to 22,000 to 500 million, it's still quite possible for the variable to take on a value of 500 million. It's varying over much greater range. And as I've just said about with the stock market, one of the issues is that if it's scale free, the fluctuations can be over a much greater range than you would expect for a normal distribution. And well, if it obeys a log normal distribution, the same thing can happen. The fluctuations can extend over a much greater range than if it's just a normal distribution. And so a power law and a log normal can be a bit difficult to distinguish. And in fact, many examples of power laws that we see in real data can often be better modeled in fact as a log normal. So that's all we'll say about the log normal for now, but later on when we come in the non-mathematical, the actual history parts of the course, we will see some examples of log normal distributions, and we'll discuss their properties in more detail then. But that's the main takeaway, that with a log normal you get that same kind of thing that you get with a power law, very great range of variation in the value of the variable. And as theoretical historians, we need to be aware of this, so that when we see data with a large range of variation, we might think initially, power law, but actually it could be a log normal. So you need to be aware and be ready to check for that. Okay, and the last topic I said we'd discuss in this lecture on distributions is that of hypothesis testing. And I said this is where we want to know whether two sets of data are possibly drawn from the same distribution or definitely drawn from different distributions. So I gave the example, if we saw that Christian countries, or a higher proportion of Christian countries, are democratic than non-Christian countries, is that definitely something different about Christian countries, or is that just a matter of chance? Is it that the probability is different for Christian countries, or is it it's the same but just by chance Christian countries happen to have more? Another example we might have is where if we're studying the lengths of the reigns of monarchs in two different countries, country 1 and country 2, we might find that in country 1 the mean length of the reigns of the monarchs is 12 years and the standard deviation is 3 years, and in country 2 the mean is 15 years and the standard deviation is 6 years. The question then is this a real difference between country 1 and 2, or is the dynamics of kingship are the same in both countries and it's just by chance that the particular reigns that we looked at give a different mean and standard deviation? And statistical software gives us ways of entering our data and comparing it and asking whether these could be drawn from the same underlying distribution. And when we say the hypothesis testing, the standard hypothesis is that there's no difference. So we're testing the hypothesis that there's no difference. So what we're interested in is the probability that this could occur by chance. This seeming difference between the two countries, a difference in the means, a difference in the standard deviations, could that have occurred just by chance because they've got the same underlying mean and standard deviation? And when we just select a few out, we get a particular mean and standard deviation that looks different just by random chance. So we're asking, what is the probability of this occurring if there were no difference? So it's sometimes called the p-value. The probability of getting this result, this difference, by chance, if there is no underlying difference in the distributions of the reign lengths in the two countries. And typically 5% is considered significant. So if the probability of this occurring is 5% or less, then it would be considered significant. 5%, so that's 1 in 20, or also probability of 0.05. So if the chance of this occurring on the hypothesis that there were no difference is just 1 in 20, then we say, well, that's not very likely, is it? What's the chances? You throw a 20-sided die, what's the chances of it coming up 1? It's pretty unlikely. So this is unlikely to have occurred by chance. So the hypothesis that there is no difference is rejected. And that's what what you're really looking for. To find that there's no difference, well, then that's not very interesting. That's the boring answer. But if you find that it's statistically significant, you can say, I've discovered something. The way kingship works in country 2 is different from in country 1. It produces these higher reign lengths, and we therefore need to see what it is about country 2 or its social institutions that produces this difference. But the problem with that is that it could still be due to chance, 1 in 20. And there was a paper produced at why most scientific results are wrong, is because there might be 20 research projects, and by chance one of them will find a statistically significant result, in inverted commas, just by pure chance, because there is a 1 in 20 chance of finding a statistically significant result, even though there isn't really a difference. Now those 19 other projects that didn't find a statistically significant result, well, they'll just shelve their data, they'll just shelve the results, because there's no, nobody who's interested in publishing a paper that we didn't find anything. And only the one in 20 that did find something, even though it's spurious, even though it's just occurred by random chance, will submit their paper and get it published. Oh, that's interesting. It's the statistical difference there, less than 5%. Well, that's not very likely, is it? So this looks like a significant result you've got. So that will get published. But in fact, it's really just that 1 out of 20 studies that by chance happen to find a difference, even though it's just like somebody happened to be lucky and throw a 6. Okay, I'm now going to give a specific example of hypothesis testing, so we can see how it actually works with what's known as the chi-squared test. Chi-square or chi-squared, I tend to say, but some people call it the chi-square test. And there's a function for this, for example, in Excel. I'm going to take you through how it works, but you would typically do this not manually, but in a spreadsheet if you're using Excel, using the function chi-square.test. And I'll put up some data that we can work with. Okay, so here's some imaginary data based on a theoretical historian who's studying the incidence of different types of political violence in 3 different types of polity, or societies with different political institutions. So the 3 different types of society are democracies, monarchies, and dictatorships. And the types of political violence are civil wars, coups, and revolutions. And what they've done is recorded the number of different types of each type of political violence in each type of polity, or society with political institutions. And so we've got these numbers. So for democracies, they had 11 civil wars, 6 coups, and 4 revolutions, giving a total of 21 different episodes of political violence. With monarchy, we've got some different values, and there are 26 in total. And for dictatorship, we've got, again, different values here, and they add up to 28 incidents of political violence. And then the grand total here is 75, and also we've got the totals of civil wars, coups, and revolutions in the 3 different types of polity. And someone might look at this data and say, well, it looks like there's some kind of difference going on here. In dictatorships, there were 7 civil wars and 14 revolutions, whereas in democracies there were 11 civil wars and only 4 revolutions. So, pretty much reversed there. So it very much looks like the fact that civil war is more likely in democracy, and a revolution is more likely in a dictatorship. So, we've discovered a result, and we can go and publish that. But we need to do some hypothesis testing. Are these apparent differences actually statistically significant? Could these differences, apparent differences, have occurred by chance? That, in other words, the chances of civil wars in dictatorships are the same as in democracies, and it's just purely by chance that here there would just happen to be fewer of those and more of those. So that is where the chi-squared comes in. And we call this, the values in this table here, the observed. That's what we've observed. Now remember, our hypothesis is that there is no underlying difference. And what we want to do is prove that hypothesis incorrect, or at least that hypothesis has such a, these results would be so improbable with that hypothesis that we reject the hypothesis. So what we want to do is find the expected values, what we would have got if these are obeying the same distribution, if the chances of civil war were the same in every type of society. So we're going to draw up another table, the expected values, to compare with the observed. So let's have a go at that. Okay, here I've constructed our expected table. So we've got the same basic design: civil wars, coups and revolutions, democracies, monarchies and dictatorships. And we're going to, or we require that the totals should be the same in each case. So there were 21 events in democracies. There should still be in our expected table 21 events in democracies. And also there were 30 civil wars, so there should still be 30 civil wars. But the numbers we're going to put in these boxes now are what they would be if the proportions were the same for each of the different polity types, rather than being different as here. If they were all drawn from the same distribution, on average we would expect them to be distributed in the same proportions. So as in the proportions of the totals, 30 to 20 to 25. There should be the ratio of civil wars to coups to revolutions should be 30 to 20 to 25 for all the polity types. And that is how these numbers have been calculated. So for the democracy, there were 21 events, and we should expect 30 out of 75 of those 21 to be civil wars, which comes to 8.4. And then 20 out of 75 should be coups, which is 20 out of 75 multiplied by 21 comes to 5.6. And lastly, 25 out of 25 75ths of the 21 should be revolutions, and that is 7. You can see that one in your head, because 25 divided by 75 is a third, and a third of 21 is 7. So that's where that number 7 comes from. And the same for the other cells in this table. And now we want to construct the chi-squared statistic. That I should have said that is the Greek letter chi, kind of an X, pronounced with a hard h. And the chi-squared statistic is defined as, firstly we take the observed value minus the expected value. We find the difference between them and we square it. So we're not interested in whether it's positive or negative, which way it varies around the expected value, whether it's more or less. We're not concerned about that, but just how far away from the expected value it is. And we divide that by the expected value for each cell. So we then add those values up. Observed minus expected squared divided by expected. So it's going to be 11 minus 8.4 squared divided by 8.4. That's that one. 11 minus 8.4 squared divided by the expected 8.4. And then for this one, it's going to be 6 minus 5.6 squared divided by 5.6. And then 4 minus 7 and so on. So we do that for all the remaining 6 cells. And as a result of that, we get this chi-squared value. In this case, when we do all that, it adds up to 6.7. And now to work with this chi-squared statistic to work out what we should, how that compares with what we would expect given our hypothesis, we need to take account of the degrees of freedom. Degrees of freedom, which is how much leeway do we have in choosing our values here. Well, if we start with the first lines of democracy, for the number of civil wars, we could put any number we like in there. So that's 1 degree of freedom. We could also put any number we like in there for the coups. But because it's got to come to 21, we can't put any number we like in there. We've got to put in the number that makes this come to 21. So we can choose that freely, we can choose that freely, we can't choose that one freely. So we've got 2 degrees of freedom there. And then when we come down to the monarchy, again, we can choose anything we like there, we can choose anything we like there, but we have to choose this one to make it come to 26. So we've again got 2 degrees of freedom. So we've got 2 degrees from democracy, we've got 2 degrees from the monarchy line. And what about the dictatorships? Well, if we've chosen that freely and that freely, we can't choose this one freely because it's got to come to 30. So we've got to choose that number to make this add up to 30, given that whatever we've chosen for those. So there's no degrees of freedom there, nor is there any degrees of freedom there, and nor are there any degrees of freedom there. So we get no degrees of freedom from the last line. So the degrees of freedom equals 4. So the 2 pieces of information we need are our numbers of degrees of freedom and our chi-squared statistic. And back in the old days, you would have got a book of statistical tables which would allow you to look up for degrees of freedom the chi-squared statistics for particular probabilities, and you would find the chi-squared with 4 degrees of freedom and for 95% probability is had it down somewhere 9.49. So what this means is that in 95% of cases, the chi-squared with 4 degrees of freedom, the chi-squared would be 9.49 or less. Only in 5% of cases would the chi-squared statistic be more than 9.49. Well, in our case, it's only 6.7, which is less than 9.49, so it's within the 95%. It's certainly not in the 5% of cases where it's more than 9.49, because we're not 9.49. So if it were more than 9.49, we'd say there's only 5% chance, there's only 5% of cases where it will be more than 9.49. And therefore it's statistically significant with a p-value of 5%, or at the 5% level. There's only a 5% chance of having this these data in the table. But in our case, we're not saying that because it's not bigger than 9.49, it's less than it. So it's within what could occur in 95% of cases. So we reject the hypothesis. So we don't reject the hypothesis. We have to accept that these values could occur by chance, even though that might at first seem improbable. Now, I said that's what you would do in the old days with statistical tables. You'd look up the degrees of freedom and you'd look up your chosen percentage probability, and you'd find a chi-squared statistic and you compare that with what you've got. But with the Excel chi-square test, you just feed it the observed values and you feed it the expected values, and it throws out a probability that you could get those observed values if these are the expected values. And I think with these particular figures, again, I've got it written down somewhere, is the XL chi-squared test function gives 0.154, or in other words 15.4%. That is, there's a probability of 0.154 or a 15.4% probability, or in 15.4% of cases you could get these values with this underlying distribution. And so 15% probability is quite a high probability. It's not, 1 in 20. It's which would be only 5%. This is 3 times that. Three chances in 20 of getting this with this underlying distribution. So not significant. Not significant anyway at the 5% level. So again, we fail to reject the hypothesis. And that is how you do a chi-squared test. That is hypothesis testing. So if you have you're doing this kind of research, you have this kind of data, you think you've got a significant pattern there, a chi-squared test is going to tell you whether you really do or not.